students. We are resuming our discussion of capacitance. In the last discussion, we talked about various combination of capacitors, and I have selected a few questions from the past papers for discussion. And this is hopefully for the last time we are talking about this topic, capacitance. With this discussion, it will be concluded, it will be finished, and we'll be in a position to start the new topic. Hopefully, after next week, we'll meet face to face with the new topic. One of the questions that appeared in recent exam was two capacitors connected side by side. They are connected in series, and then there are two capacitors connected parallel to each other. The capacitance of these two are known, they are identical. Each one has 3 microfarad of capacitance. And these are the points A, B, which are connected to a battery of known voltage, and that is given, this is 12 volt. So a 12 volt battery is connected across this combination of capacitors. If the total capacitance of this combination is known, see, total is known to be 4 microfarad. What is this capacitance and this capacitance equal to? These are two identical capacitors connected in series, and we want to know the value of C. So we apply a simple formula here. If you remember, these two are added in this manner, 1 over C plus 1 over C, and these two are added to be 6 microfarad, and this 6 microfarad is again in series with this, so 1 over 6. This all is equal to 1 over 4. So whatever answer I have for C, I will have in microfarads, because I'm not writing micro along with 6 and along with 4. So my answer to C will be in microfarads. When I simplify these two, of course, it will be 2 over C. And on simplifying this simple arithmetic, this reduces to C equals 24 microfarad. You can simplify this to find C, and it comes out to be 24 microfarad. So we have a 24 microfarad capacitor here, a 24 microfarad capacitor here, and then 3 microfarad each connected in parallel. The question they usually ask is how much charge this capacitor will store, how much charge will this capacitor store. Various capacitors may be asked about. In this question, they are asking what is the total charge delivered to this combination of capacitors. So let's call this Q total. The total charge is always calculated using the total capacitance and the voltage applied across that combination. Q is equal to C. V is the formula that we have always used, and this is the total capacitance involved here, which is 4 microfarad. So 4 into 10 is power minus 6 into 12. So this becomes 48 microcoulomb of charge that this combination of capacitor uh, will have stored on this. Of course, it can be different if we have different capacitors in parallel, but in series combination, we learned in the beginning that 48 microcoulomb, which will be delivered, let's say, to this side of the capacitor. If I have a positive on this side and negative on this side, it will be easy to understand. We have 48 microcoulomb actually stored here. Minus 48 will be here. Then positive 48 microcoulomb induced here, then negative induced here, and the same 48 microcoulomb will be stored by this combination together, these two. But since they are connected in parallel, so 48 microcoulomb will divide up exactly into two halves, and each capacitor will take 24 microcoulomb. So if they ask what is the charge stored on each plate or on one plate of this capacitor or on this, the answer is 48 microcoulomb. But what if they ask to calculate the charge stored on one of these two capacitors? That simply means 48 divided by 2, because they are identical capacitor, so it will be exactly 2 halves. So 24 microcoulomb of charge will be stored on this and on this capacitor. Another question, similar of course, let's discuss that question as well. In this capacitor, this arrangement, we have three capacitors again. One capacitor is known to be 3 microfarad. This is a capacitor which is 4 microfarad. And this one is the capacitor X. And we want to know its capacitance. One thing that is known is the total capacitance of the combination. So of course that makes the things easier. These two are added, that means 1 over 4 plus X. So X will be in microfarads, plus 1 over 3. So these two are in series. 4 is added to X because these are in parallel, and when you have added them like this, these two are in series, so 1 over this plus 1 over this. This all is given to be 1 over 2. The total capacitance of this combination is given to be 2 microfarad. So what is this X equal to? This X is to be found now. So let's simplify it. This 1 over 4 plus X will be equal to 1 over 2 minus 1 over 3, 1 over 2 minus 1 over 3. And this becomes 1 over 6. All this reduces to 1 over 6. All this is 1 over 6, which simply means 4 plus X is 6 due to this equated to this. So 4 plus x is equal to 6 simply means x is equal to 2. So this capacitor comes out to be 2 microfarad. So one step. Now, if we apply exactly 9 volt across this combination of capacitors with the positive side on this and negative on this, how much charge will be stored on this? But before we calculate the charge on it, we are required to calculate the potential difference across this. What will be the value of potential difference across the 3 microfarad capacitor? So potential difference across 3 microfarad capacitor will be calculated with the help of the ratio method here, because we know this 9 volt is to be divided between these two combination. You have 3 microfarad here, and then you have 4 plus 2, 6 here. This is twice as much. So I told you last time, if capacitance is twice as much, voltage is half as much. So this 9 will be divided into 2 parts, and this will take half as much voltage or potential difference as compared to this. So this, out of this 9 volt, 3 will be available for this and 6 will be available for this. If capacitance is 3 and this capacitance is 6, voltage is 6 for this and 3 for this. So the product remains the same because they will be on series. Q is equal to CV will be the same. So because Q is equal to CV, so if 3 is the capacitance of this, it will take 6 volt across this. Therefore, 6 volt is your answer. So you have a reasoning like this. Since this combined 6 microfarad capacitance is in series with this, and this capacitance is twice as much this, so this will take half as much potential difference as compared to this one. So this is 6 volt across this out of this 9 volt available. So this is how you reason when you decide how much potential difference will be available across this. Once you know that this will have 6 volt available across this 6 volt, it will be easy to calculate the charge on one plate of this same capacitor, of the same capacitor, of this capacitor. That will be C into V, therefore this will be 18 microcoulomb. Now this 18 microcoulomb will be stored by this combination also. If they ask us what charge on one plate of the capacitor of the capacitor X will be equal to, then the 18 microcoulomb will be divided into 2 parts actually. Again, larger capacitance, which is twice as big as this, will take the larger share of this charge. So 4 microfarad capacitance is expected to take twice as much charge as this capacitor. So what we expect is the larger one will take 12 microcoulomb and this capacitor will take 6 microcoulomb. So answer to this question, that is, what charge will one plate of this capacitor X have on it, is 6 microcoulomb, because out of this 18 total microcoulomb charge available, this will take half as much charge as this because its capacitance is half. The potential difference, of course, is same across the two, which we calculated to be 3 volt. With that 3, we can also calculate it to be 6 microcoulomb, because 3 multiplied by this 2 also gives us 6, and that same 3 multiplied by this gives us 12. So we can independently calculate this using the same formula, Q is equal to CV. And now we come to the last part of it. In some questions, you will see a graph between charge and potential difference across capacitor, and that is often like this. If we have Q on this side, usually measured in millicoulomb, and this is voltage on this side measured in volts. On this scale, on this side, we could have a scale like 5, 10, 15, 20, 25, and so on. And on this side, it could be 1, 2, 3, 4, and so on. It's measured in volts. As we increase the potential difference across a capacitor, if it has a sufficient capacitance, it will go on storing more charge across this. Or conversely, when we store more charge in a capacitor, the potential difference that it will show will be larger. Either way, it will be a straight line passing through the origin, because if there is no potential difference across a capacitor, then obviously it is not having any positive and negative charges on it, on the opposite plates on it. If this line, as you will see in some of the past papers, this line is not passing through the origin, that of course indicates a systematic error. So sometime this is slightly below this, it has a non-zero X intercept or Y intercept, that is systematic error. Otherwise it should be through the origin. That simply means that if they ask if this Q is directly proportional to V, yes, that should be, because it's a straight line passing through the origin. What is the capacitance of a capacitor which represents this graph when we plot this charge stored on it against the potential difference? So clearly, let's say I'm using these same values. This is 4 volt exactly, and this is, to make it simpler, let me bring it here. So suppose it's a graph like this, exactly through the origin and here. So it is 20, C is equal to Q, the C is equal to Q over V. This is what the formula is. So Q over V is the gradient, and that should be equal to the capacitance So 20, which is in milli, so minus 3 divided by 4. This is what the gradient is, and that is should be the capacitance of the, if I simplify this, this is 5 into 10 is power minus 3 farad. Usually this is expressed in microfarad, so this should be 5,000 microfarad of capacitance. So any capacitor which have a straight line like this and with 4 volts available, it stores 20 millicoulomb of charge on it, its capacitance should be 5,000 microfarad. And if we go on increasing the value of this voltage, and if the capacitance allows it and we can store more charge on it, what will be the additional energy we can store on it? That again is a simple formula. We have already discussed it. The idea of this question was to show you the relationship between Q and V. Of course, you already know, but there are several questions in which you have to calculate the gradient, and then the subsequent calculations are done with the help of it. So once we know this 5,000 microfarad now, what will happen if I continue increasing the voltage across this, and if it can store more charge on it, what will be the additional energy it can store on it? Let's do it. If we increase the voltage, suppose V1 was 4 volt, but we increase it to 9 volt. What will be the additional energy stored? So additional energy delta E will be 1/2 C V2 square minus V1 square. So 1/2 into 5,000 microfarad, so minus 6 into, this is 9 square minus 4 squared. So this is how you calculate. So whatever comes out, most probably this will be of the order of 10 is power minus 2 joules if you simplify it. So this is all for today's discussion. Some of the questions selected from the past papers I have discussed. I hope I have discussed them in enough detail, so you can find many questions easy now. Try to finish this all. I'll share with you a worksheet about this. And you have ample time to complete all the backlog if you have not done a lot of work so far. After next week, hopefully, we'll see each other face to face. Thank you.